Let's say I have a bucket of water here. Now when water evaporates, it cools down. If you just leave the water here, the water on the table on its own, without doing anything, it's not very obvious. But if you blow at it, or if you splash some water on your hand, and when the wind blows, or you blow at your wet hand, you'll feel cool almost immediately. Why is that? Why does water cool down when it evaporates? This is the question I want to look at now. Right? Why does a liquid, so it can be other liquid, not just water, but I'll use water as a familiar example. Why does a liquid cool down when it evaporates? Now the short answer is that you need energy for the liquid to change into a vapor, just like when you boil water. So if the liquid just evaporates, it has to take the heat from itself or from the surrounding. So that's why the liquid cools down. But what actually happens? How does this happen in terms of the movements of the molecules and atoms? Now remember from our ideas about kinetic theory of gases, remember that temperature is related to kinetic energy of the molecules in a gas. And we've extended this idea to liquids and solid as well. The higher the temperature, the higher the kinetic energy, so that the molecules move faster. And then of course there is potential energy involved because of attraction between molecules. But what happens in an evaporation? Now the thing about evaporation is that it's not boiling. In boiling we would apply heat either as a fire or electric heater. We would apply heat and then temperature increases and it boils. But evaporation is different, right? Evaporation, what are the characteristics of evaporation? So evaporation means that you don't apply any heat, alright? It is not heated, right? You don't heat it directly, and it can happen at room temperature, right? At room temperature, it can just happen. As long as you leave it on the table, it happens at any temperature. Actually, room or any temperature. So what's going on? Right, let's think about the molecules and atoms. There are lots of molecules in the water. Now I'm just going to look at those molecules that happen to be near the surface of the water. These molecules, like all the others, they are moving randomly, and there is a range of kinetic energy. So the molecules, right? There's this idea that the motion of the molecules are random. So you can have some have more velocity, some have less, some go left, some go right, some go up, some go down. Right? Random motion, random speeds. They have random speeds and direction. But of course, the average of the kinetic energy is related to the temperature. Okay, but apart from the average, they're just banging around quite randomly. Okay, random speeds and direction. So this means that some have more kinetic energy, some has less. Now those in the surface that just happen to be moving in an upward direction. Alright, there must be some, surely, because it's all random. And those that happen to have a larger kinetic energy might just be able to overcome the attraction from their neighbors and escape. Now you can imagine that this might be just a very small fraction of all the molecules. We're talking about having large enough energy. Right? Most of the molecules would be maybe closer to the average, but some maybe just a tiny fraction that happens to have bigger energy and happen to be moving upwards would be able to escape. So it's all quite random, but on average we would expect that there would be a very small percentage that can happen. So those that just happen to be going up and are fast enough will escape. Okay, but what happens when those escaped? The molecules left behind. Let me write down this point. This is an important point in the answer. Okay, right. Those that happen. Maybe I'll emphasize this idea of randomness. Those that by chance move upwards, right? Not only move upwards and have enough, not just move upwards, but and move fast enough, meaning that they have enough kinetic energy to overcome the attraction. All right, escape into the air. What happens then? Now, then those molecules which remain behind must therefore have a smaller total energy or average energy. Okay, because the energy must be conserved. Okay, if it has lost some higher energy molecules to the air, right, what remains must have less energy. So the water that remains, right, would have, it would, that remains has less less energy, and therefore lower temperature, right? Less and therefore lower temperature. And that explains why when a liquid cools down, that a liquid cools down when it evaporates. Okay, and the simple answer is that it loses those with higher kinetic energy, those molecules with higher kinetic energy, to the air. And you already know that if you splash water on your hand and blow at it or put it in the wind, your hand would feel cool immediately. Or if you are feeling really warm, you can splash some water on your face or your body and you'll feel cool, right, as they evaporate. And in the extreme case, we can actually attach a pump, right? Attach this to a vacuum pump and pump away the water vapor, and that would actually help the water to evaporate. Alright, whether we use a vacuum pump or if you blow some air at it. Yes, in fact I should talk about this. Now, if I blow at this, maybe with either with a fan or just blow at it, okay, it will help the water to evaporate faster. Why is that? Why is it that when you blow at the water it can evaporate faster? Right. The reason is this. Now, as I've said, the water molecules, those that happen to be moving up, would escape. Now, when they escape, they don't just go out all the way in a straight line and never returns, right? But that would happen if we are in a vacuum or if we are in outer space. But because there are lots of air molecules around, those water molecules that happen to jump out into the air, they would most likely knock into some air molecules, some oxygen or nitrogen molecules that are everywhere. Okay. Most likely knock into them and bounce around. All right, so they'll most likely be bouncing around. So this means that they would sort of, they would sort of slowly spread out, but in the beginning, they would be bouncing around quite a bit as they diffuse outwards. Now, as they bounce around, it is therefore, since the bouncing around is quite random, it is therefore possible for some of the water, right, after moving around randomly, to just happen to move downwards and go back into the water. Right? So it's possible simply because it's all random motion and some moves up, some moves down, some left, some right. So because of this, it means that some of the water vapor molecules that escaped will actually come back unless we remove them. And how can we remove them? Well, the easiest way is to blow at it. All you need is to keep blowing at it. Then any water molecule that happen to jump out into the air, right, before it has a chance to bounce around and come back into the water, you would blow at it and remove it and just move them away so that they will never actually come back again. And as a result, if you blow at it with some wind, the water molecules would never come back, so there will only be water molecules coming out. No water molecules come back. So in that sense, and in that way, the rate of evaporation would increase, simply because no more water molecules would come back.